Hello! Welcome to today's lesson on how work is done when stretching or compressing a spring. Our plan for this lesson is as follows. We'll begin by reminding ourselves of the concepts of work and deformations. Next, we'll introduce a trampoline analogy to break down the stages of energy transfer and work in compressing and stretching. Finally, we'll introduce the calculations which describe these stages and run through some worked examples to consolidate our knowledge. So far, you have learned about Hooke's law and the concepts of elastic and inelastic deformations. You understand how forces cause objects, like springs, to deform and return to their original shape when the forces are removed if the deformation is elastic. Building on this foundation, we can now explore how the deformation of a spring involves doing work, how energy is stored and released, and how to calculate elastic potential energy. This will advance our understanding of energy transformations and conservation in physical systems. When we apply force to a spring, whether to stretch it or compress it, we are doing work on the spring. Work in physics is a measure of the energy transfer when a force moves an object through a distance. The equation for work done equals force multiplied by distance along the line of action of the force, and this is measured in joules. To help you visualize this, let's use an analogy. Imagine you have a trampoline with its surface flat and relaxed. This state is similar to an uncompressed spring, which is its natural length without any external forces acting on it. Now, if you place a ball on the surface of the trampoline and start pushing down, you are applying a force. This force causes the trampoline's surface to deform, just like a spring deforms when you compress it. The more you push, the more the trampoline stretches, and similarly, the more the spring gets compressed. As you push down, the trampoline stores energy in its stretched fabric. This energy is stored as potential energy, specifically elastic potential energy. The same happens when compressing a spring. The work done on the spring by compressing it is stored as elastic potential energy. When you release the trampoline, it springs back to its original shape, throwing the ball into the air. This action is an excellent way to see energy conversion. The stored elastic potential energy is converted into kinetic energy, which propels the ball upwards. Similarly, when you release a compressed spring, the stored elastic potential energy is converted into kinetic energy. We can quantify the elastic potential energy stored in a spring using the formula that we've seen previously in the energy module. Elastic potential energy equals 0.5 multiplied by spring constant times by extension or compression squared. The spring constant measures the stiffness of the spring. It is a value that tells us how much force is needed to stretch or compress the spring by a certain amount. The value of K is specific to each spring and is measured in Newton meters. The extension or compression refers to the distance the spring is stretched or compressed from its natural length. It is measured in meters. Due to the principle of conservation of energy, the work done on the spring when stretching it or compressing it equals the amount of elastic potential energy stored in the spring, provided the spring is not inelastically deformed. In simple terms, no energy is lost, and all the work you do is effectively converted into stored potential energy in the spring. With this established, let's apply what we've learned to a few specific problems to consolidate our new knowledge. Problem 1. A spring with a spring constant of 25 Nm is stretched by 0.1 meters. Calculate the elastic potential energy stored in the spring. First, we identify the values. The spring constant equals 25 Nm and extension equals 0.1 meters. We can apply the formula for elastic potential energy, which is the elastic potential energy is equal to 0.5 times by the spring constant times by the extension squared. Then substitute the values into the formula. The elastic potential energy equals 0.5 multiplied by 25 x 0.1 squared. From this, we can calculate the value. The elastic potential energy is equal to 0.5 multiplied by 25 multiplied by 0.01, which equals 0.125 joules. So the elastic potential energy stored in the spring is 0.125 joules. In problem 2, a spring with a spring constant of 40 Nm is compressed by 0.15 meters. Calculate the elastic potential energy stored in the spring. First, we identify the values. The spring constant equals 40, and the extension equals 0.15 meters. We will then apply the formula for elastic potential energy and substitute the values into the formula. From this, we have the equation Elastic potential energy equals 0.5 multiplied by 40 multiplied by 0.15 squared. When we work this out, we get our answer, which is the elastic potential energy is 0.45 joules. In our last question, a spring with a spring constant of 16 m is stretched by 0.25 meters. Calculate the elastic potential energy stored in the spring. As always, we begin by identifying the values, which is a spring constant of 60 nm and an extension of 0.25 meters. We can use our formula for elastic potential energy by substituting in the values, which gives us the equation. Elastic potential energy equals 0.5 multiplied by 60 multiplied by 0.25 squared. When we calculate the value, we get our answer, which is 1.875 joules. So, the elastic potential energy stored in the spring is 1.875 joules. By working through these examples, you can see how different values for spring, constant, and extension compression affect the amount of elastic potential energy stored in a spring. This practice helps solidify your understanding of the concepts and the formula used to calculate elastic potential energy. In today's lesson, we examined how work is done when stretching or compressing a spring. We learned that applying force to a spring changes its shape, and the work done on the spring is stored as elastic potential energy. We used the trampoline analogy to visualize how this stored energy is later converted to kinetic energy when the force is removed. We also discussed the formula for calculating elastic potential energy, which is 1/2 the spring constant times the extension or compression squared. This formula helps us quantify the energy stored in a spring. Additionally, we highlighted the principle of conservation of energy, showing that the work done on a spring equals the stored elastic potential energy, assuming no inelastic deformation occurs. By understanding these concepts, we gain deeper insights into energy transformations and the behavior of physical systems involving springs. Watch the rest of the GCSE physics course at Sophos Education.